Thank you very much for that introduction. Thanks very much to the organizers for organizing this nice conference. It's great to be here in this beautiful place with so many interesting people from different fields, all under this umbrella of many-body photonics. So I want to talk about some recent theoretical work that we've been doing which relates to these systems of cold atomic gases trapped near photonic crystal waveguides. And these are kind of experimental platforms that have been being developed in the last few years. And they enable some new sort of dimensions for what we can study with these systems of cold gases. So just to begin, I'll just mention that I'm from Derek Chang's group at ICFO. That's in Barcelona. So if you want to come and visit us, this is a... Is it not full screen? It's a nice place to come and visit, and at the moment Derek's group is mostly working in this sort of field of these atoms coupled to nanofibers. So that's kind of the main part of our work at the moment, but there's a lot of other dimensions as well. In this work, Tommaso Canova and Marco Manzoni have been involved as well, so they're part of the work. And then we have quite a strong collaboration with Jeff Kimball's group at Caltech, who are doing actual experiments in this regime. So just to motivate why you would want to trap cold atoms near these photonic crystal waveguides, it goes back to just the general idea that we're all here. We want to couple atoms strongly to photons and do that at the quantum level so that it's not like we're sending a massive field to get this coupling. We want to really send in individual photons and see some effects at that level. And so the sort of traditional method of doing this is to use cavity QED, and that's a very powerful method. But if you study that system, you'll soon see that the best parameters come out of that system when you make the mode volume of the photonic mode, which is interacting with the atom, very small. So it naturally leads to kind of nanophotonics. And we've now got quite a nice array of tools in this nanophotonic world. And so it was one kind of key experiment which has motivated a lot of work is this nanofiber experiment that Peter Zoller was talking about this morning by Arno Ruschenbottel and his group. And there, you stretch out this fiber until part of the fiber is very thin, about the same scale as the wavelength of the light that you're trying to put through the fiber. And then when you put light through this fiber, it can have an evanescent mode outside the edges of the fiber. And in that place you can trap atoms, and then once you've trapped them there, you can also couple to them just by putting light into the fiber. So you get this nice system where you can get two things at the same time. You get an atom trap, which is this evanescent mode of the fiber, and then you also get quite a good coupling between photons that you put into the system. So you can talk to the individual atoms if you want to. So that's very nice. And then more recently we have these experiments where instead of just a plain sort of fiber without any features, you introduce this idea of a kind of periodically modulated fiber, which is what I'll call a photonic crystal waveguide. So there's two experiments that have been done. One at Caltech, which is the group that we're mainly collaborating with, and then also Misha Lukin's group at Harvard also has this kind of system where you have a fiber which has some sort of photonic crystal property to it. So why would we want to do that? Why would we want to put these photonic crystals on the thing? Does it give us anything more than what we originally had, which was this cavity QED system, which was very good for coupling atoms to photons? So do we get something more from that by going to these nanophotonic systems? And I hope that I can show you in this presentation that the answer to that is yes, and that it opens up new opportunities for many-body physics, so we can engineer interactions in these systems between atoms, And then there's, obviously you can use that as a quantum simulator maybe. And then later on I'll show you about how we can maybe use the system to create interactions between photons and see some interesting things that happen there. So just to take a step back and remind ourselves what exactly is this sort of photonic crystal waveguide. So what we have initially is just a waveguide, which is just some dielectric, which has a higher refractive index than the medium around it. And then that allows you to guide light. So if you put in some light into the system, then it, through total internal reflection, gets stuck inside this waveguide and gets guided to the other end. So that's good. Now what happens if we introduce some periodic modulation to the system? Well, you now get this, what I call a photonic crystal waveguide. And so this may continue to guide some modes of the light that you put into it. So you may put in some frequency and you still see a waveguiding nature where it comes out the other end. But for other modes, you might see that light is completely reflected from the system. And this occurs as light enters the system. It sees these kind of changes in refractive index, and it can sort of bounce back and forward inside this medium. And that for some particular wavelengths of light, which are sort of they have a relationship with this lattice constant structure of the photonic crystal, then the reflected light gets coherently amplified. You get constructive interference in the reflected direction and destructive interference in the forward direction. And that means it's just like Bragg physics. You get this system acts as a good mirror for some particular wavelengths of light. And then this is kind of analogous with atoms moving in an atomic crystal, and you get the same things that you would get in that system, and that you get a band structure for the photons propagating through this photonic crystal waveguide. So the important thing to note here is that at this particular frequency where this gets reflected, you get this opening up of a band gap for the photons. And another thing that I guess will matter for later on is that even though this beam might be being completely reflected, you still get this kind of evanescent tail which goes into the fiber of the field. So it's not that it just stops right here. It's sort of going in, but then getting pushed out again. So we can naturally use that idea of a reflection to create a cavity, which a cavity, all it is putting two mirrors together and then putting something in the middle. So if you put a photonic crystal on one side of your system and a photonic crystal on the other side of the system, then in the middle you can expect that you can get some sort of localized cavity light mode of this structure. And then I can couple that to an atom, and then I have my traditional cavity QED, which is described by the Jaynes-Cummings model. So that's good, and in fact that's what they're doing or have done in Misha Lukin's group, and they've done it to such a, I mean, the great thing about the system is that what you're really doing now is, because this is on a scale of less than the wavelength, this length scale is really at the kind of limit for cavity QED. So it's hard to think of how you would make a smaller cavity. So that's really getting you right to the edge of what you can do for coupling an individual atom to an individual photon. But I told you that maybe there's more to this idea than just having really good cavity QED. So where does that idea come from? Well, so suppose we take just a completely uniform photonic crystal. So to make the cavity, I had to remove a hole in the middle, a sort of defect cavity. But now I've just got a completely uniform photonic crystal. And then if I put an atom nearby that photonic crystal so that it couples to this thing, and then I excite it by driving it. So now this atom has absorbed a photon. And what I do is I drive it within this band gap in the band structure. So now it's kind of detuned from this lower band here by some delta. And the atom would like to emit a photon into the waveguide, but it cannot, because, as I said, in the bandgap, the propagation is not allowed. So this propagating mode is not allowed. But we can still use this kind of evanescent tail that would happen in this case. And so what you get is this new physical object, which is an atom photon bound state. So this is like a localized photonic cloud, which kind of sticks with the position of the atom and follows the atom around. And so that's a new sort of state that you wouldn't achieve in a normal atom coupled to a fiber case, but now because you've added this photonic crystal nature, you get this new atom photon bound state. And then we can use this this photonic cloud to then mediate dipole-dipole interactions between atoms. So if I now put another atom here, then this one is excited, but it still has this photonic cloud associated with it. And then because this one is in the range of this photonic cloud, it can then absorb that, and you can get this flip-flop dipole-dipole interaction between the atoms. I guess the unique thing here over the just normal fiber case is that there's no dissipation. Like the photons do not leave the system through the fiber, whereas in a normal non-photonic crystal fiber they would also be able to leave. So you would have this flip-flop interaction, but it would be associated with some loss. Also, you get some spatial dependence of the interaction. So it's not just a uniform interaction depending on the position. You may note that because this is an exponentially decaying sort of evanescent field, that's the nature of those interactions. They also have evanescent and exponential decaying nature. And you might say, well, I've written up here long-range interactions, that's not long-range. Well, it's not, that's true in the thermodynamic limit, but for the purposes of the experiments that are trying to be done, these interactions can be, the length scale associated with it can be much longer than the actual length scale of the interaction. So you put all your atoms in a box where the interactions can be much longer than that. Another thing about these interactions is they can be tuned. So I said that we drive within this band gap near the band edge, and depending on where you do that, where you make this excitation relative to this band edge, that will alter the size of this photonic cloud. So as we get closer to the band edge, then these photonic clouds can get larger. It makes sense that you're getting closer to being a propagating photon as you get closer to the band edge, so that this cloud stretches out. And so in that way, we can tune the interaction in length. So this is kind of the basis for what I'll go on to talk about next. But just to sort of sum up this kind of part is that these photonic crystals allow you to sort of engineer these interactions in an interesting way. And we've summed this up in this paper here with our experimental colleagues, Jeff Kimball and Qianlang Hung. So one thing you can, I showed you a very basic picture of how these interactions occur, but if you now apply some of the tools of quantum optics using more levels and other driving fields, then you can now take these basic flip-flop interactions and then engineer them into more complicated interactions. So for example, we show in the paper that you can make this Ising type interaction with now long-range interactions. And you can tune the shape of this interaction by using different driving fields. So we showed that you can make a weird sort of polynomial dependence like this one, which is unusual. And another thing to note also is that these atoms are not really trapped at particular sites, or they may be in an optical lattice, but they also have this phonon degree of freedom. So it's not just we're not just creating a spin model, but we're also creating a spin model with these coupled to the position nature of the atoms, which may be some quantum phonon or something. So you have that extra degree of freedom in the system. So that's nice. We have that those ideas. So what I'd like to talk about now is that now can we use those ideas to do something interesting with photons in the system. So we have these fiber systems where you can easily couple photons into the fiber, and then they interact in a large way with the atoms along the fiber. And then you can also have these atom-atom interactions, which are long-range as well. So can we leverage these long-range atom interactions to then create photon-photon interactions in the system? So one thing about the Jeff Kimball's experiment, which sort of helps us to do that, is the fact that this alligator waveguide, as it's called, doesn't just have one sort of fiber mode. It has a couple of base modes. So you can have one mode which will act like a waveguide for these photons that you're trying to get put into the system and make them interact, and then another mode to mediate these long-range interactions between the atoms. So that enables us to do that. And okay, so just to get an idea of sort of a toy model to build up intuition of how these photon-photon interactions might work, we'll just consider this a simple situation. So this is our waveguide, and then I have a bunch of two-level atoms, so ground and excited state, trapped along my photonic crystal waveguide. And then I suppose that I can engineer this excited state interaction. So this is a dispersive interaction where one atom being in the excited state will shift the excited state of another atom. And actually this is detailed more, I think, in Andreas's work. So if you want to talk to him, he's here. He's got a poster about using these type of interactions to create a quantum mirror which only reflects one photon and not another photon. So it's an interesting idea. So that poster is out there, I think, and you can have a look at that. But just to see what this does for photon-photon interactions, if I now have a photon which has come into my system, it's traveling through the fiber, and then it excites an atom here to the excited state, then now this atom's in the excited state, and then all these atoms surrounding it get a shift to their excited state. And then another photon in the system being over here sees a shifted atomic response than it would normally. So if I represent the atomic response by this susceptibility function, where this is the red part's the absorption and the real part is this kind of phase shift that a photon gets propagating through an atom, then all of this gets shifted because I've shifted this excited state. And that clearly is going to change how this photon is propagating in the system. And it's dependent on whether this photon is over here interacting with this atom. So that means I can get some sort of nonlinear response over a long range due to like individual photons being in the system. However, I wouldn't really want to do this with this two-level atoms that I've just shown you, just because if we look at the atomic response, it's highly absorbative when there's anything interesting happening. So there's good stuff here happening in the phase, but also I get high absorption. So if I want to do something with my photons and not lose them, then I don't really want to work with two-level atoms. I'd prefer to work with three-level atoms and put them in this lambda type configuration. And this is nice because then once I have a two-photon resonance going from G to E to S via this control field, which is a sort of coherent laser which I introduce externally, then my quantum photons, if I get two-photon resonance with this going here, then I actually get what's called electromagnetically induced transparency. So the medium on this two-photon resonance, so at this point, when this is omega is 0, then I get complete transparency of the system. And that allows me to put my photons into the system, and you can see I can propagate them through, but there's also quite a strong response. So if I was to shift this two-photon resonance, then I can get some sort of dependence on that shift for the photons to see this kind of long-range changes in the refractive index. So just to do the same thing again, except for the three-level atoms, suppose I have now an infinite range interaction. So as I was saying before, you could, in these systems with the band edge physics, you can make these interactions long range enough that they kind of extend a long way further than the actual size of your atomic sample. And so that could be approximately this kind of infinite range interaction. And I assume it's interacting between the S levels of my atoms. So now if I do the same thing, I have all my atoms along the waveguide, and then a pulse is introduced to the system, and it excites this particular atom from G to E and back down to S. Then all my other atoms now feel this interaction, and they all feel a shift lifting up this S level. And so now if I want to put another photon into the system, then it really doesn't want to travel at this original resonance frequency of the E to G transition. It now wants to do a different frequency, which is this E to G plus this extra interaction shift. And then to be self-consistent, if they both want to propagate together, so if this one wasn't here, then this one would be fine at EG. But once this one's here, then this one also gets a shift. So to be self-consistent, they need to be both at the shift in frequency. So this gives me this idea of, instead of before where for a typical EIT, I just have, it's completely linear. It's not dependent on how many photons I put into the system. If I put 1, 2, or 3, they all go through. But now I have this new system where now I put a coherent pulse into the system, and then at one particular frequency, it's more preferential for one photon to go through. If I put it in a different frequency, then 2 photons is a better idea. So that's this kind of number correlated transmission. And then, so as a kind of side note, that's a general intuition, and then we would like to model that numerically. So just to kind of say how we did that, we use this, what we call the spin model, which is related to what Peter Zoller was talking about this morning. When you eliminate the electromagnetic fields in this fiber, you can get a sort of a master equation for the system dynamics, and that reduces everything to the atomic response. So when I have an excitation in this atom, for example, it can couple out, that's loss, it's in the master equation, or it can go and talk to this other atom, and I get an effective interaction between these atoms once I've eliminated the electromagnetic field modes. So that allows me to study these systems as kind of a black box. I just have to put in my input field, and then I have this waveguide interaction Hamiltonian, and then I also have any other atomic Hamiltonian, could be my 3 levels, 5 levels, whatever, on top of that, and then I get out my output field is just obtained from the input field plus some function of these atomic coherences. So that's a nice way of modeling these systems. So just to go back to what we were doing, we had these number correlated transmissions, and then studying them numerically, we indeed see that this behavior is according to our intuition, that so this is plotting the 2-photon detuning, so how far this is detuned with respect to this interaction. So this is for single photons, part of the wave function, and this is not affected at all by the interaction. So with only 1 photon in the system, there's no interaction, so this just sees the normal response that it always does. But then for 2 photons here, we see that as the interaction changes, then so does the 2-photon detuning that you want to put the photons in. So it's representing this kind of shift that we have here. So now I'd like to do just something a little bit more, that was basically saying my interactions were uniform. Now I'd go a bit further and say, well, can we really use the tunable nature of these interactions to create something more interesting? And so this is where these photonic molecules come in. So I want to put two photons into the system, separated by some distance, and then have them interact as if they were interacting by some force. So to begin with, I showed you that if I'm driving in the band gap, then I get this exponentially decaying interaction. And then if I add another band, so I have a lower band and then an upper band edge, then actually, because of the sign difference of this detuning, the effective interaction has the opposite sign. And then these sum together, and I can get an interaction which has some sort of minimum in here. And then I'll expect that I can find some bound state of this particular potential. And so that would be what I would want to find. The other thing to note is that in EIT, you can engineer effective mass for the photons as well as giving them these interactions. So now I have a system where I have massive particles interacting in this kind of potential, and then I expect that for the system I'll now have some sort of binding frequency, which if I stretch apart this molecule, then it's they'll be like they're acting on a spring due to this this potential here. So do I see that in the simulations? And yes, I do. Which is good. So if I put this sort of 2-photon pulse into my system, into my waveguide, and I have them separated by some distance, which is so this potential will have some natural photonic separation where these 2 photons want to be sitting the distance that they naturally want to separate. But if I make that different, if I stretch them apart, so say this dotted line here is the natural separation, then I make the separation a bit larger. So I stretch out the spring. Then over time, as the 2 photons propagate through the system, I see these oscillations. And so these are just pictures of the 2-photon wave function as I am at this first point, the second point, and the third point. And so this is the position of the first photon and the second photon, and so it corresponds to them being stretched, and then this corresponds to them being close together, and then apart again. So I can indeed see this sort of molecular nature of these photons in this system. So that's it, basically. Just to sum up, I hope that I've showed you that with these new systems of these atoms coupled to these nanophotonic waveguides, we can get some new interesting physics. So in particular, these long-range tunable interactions, and also this not many-body nature yet, but towards many-body nature for photons interacting in this system. So.
Okay, thanks, James. Are there questions? Yes, please.
In general, you know that at the moment it's quite like non-moving atoms, or
In the model.
when you do the calculations, your atoms are quite like stuck at a fixed position, or
Yeah,
so what conditions would there be needed?
Yeah, I mean, so at the moment we're assuming they're sort of on some lattice. It doesn't really seem that disorder really of that lattice changes things, but yeah, we haven't done like a full quantum simulation where they have full motion. I mean, that's going to be difficult to do. But I think the fact that it seems to be, yeah, that's right.
So for photonic crystal, can you make the minimum of the bands, or minimum of the bands, like the ozone, basically? I think you have either the minimum of 0 or the ozone.
You mean like where it gets flat?
Yeah.
The
Like,
band.
does it matter where the minimum of the bands?
I mean, for me, it doesn't matter. Yeah. So you mean that the
So I guess I would have thought that the photonic, the bound photon on the atom would have a different spatial dependence, and then maybe if that changes sign or maybe the interactions could be frustrating or something. That's
Right, yeah. So at the moment, we're just being sort of very naive and saying this is the simplest possible model we can study. And this is the sort of band structure they currently have in their experiment. So I've seen, when I visited the group, there was one guy that was working on kind of changing the nature of how they design it so that they can create sort of avoided crossings in this band structure, which introduces some new things in there. But I'm not exactly sure what exactly that would mean for how the photon mode looks, or yeah. I think there is some room that you can engineer where these things happen in the band structure.
yeah, so, okay, just to so as I understand, the wave vector is even wider than tuning, right? There's less gap, so to say, of these photons, and that gives you the decay of the photons.
Exactly.
Okay,
Yeah.
so and then they don't have any internal modulation because I have a first phase configuration.
You have what?
It's just the envelope with no extra modulation system.
Well, that's not exactly true. There's also some block modulation on top of it. Yeah. Yeah. Yeah.
Can you do something similar or the same with patterns just inside of sublinear cavity?
Sorry, say again?
If you take sublinear cavity instead of photonic crystal waveguides and put some atoms there,
Yeah.
then you do similar things.
Right. So I guess if you would just have a single mode cavity, then you get this infinite range interaction, which this doesn't have this kind of spatial dependence. But I guess if you take a multi-mode cavity and then you engineer the modes correctly, then you could maybe come up with the same idea. Yeah.
More questions? No? If not, then let's thank James again.